Hello everyone, thank you for being here today. I am Riccardo Castellotti. I work as a data engineer at CERN, where I'm in the Hadoop Spark and streaming service. Today I will show you how we developed a deep learning classifier for particle physics. But first I will give you a short introduction about what CERN is and what CERN does, and how this work integrates with CERN activities. So CERN is an international organization established in 1954 nearby Geneva, so across the French and the Swiss border. Its main purpose is to develop facilities for fostering fundamental research in high-energy particle physics. And this organization is composed by 23 member states, so most of the European countries, which contribute to the budget and to define the goals of the laboratory. 3,000 people work at CERN all year long, but the community we actually serve with our facilities is much bigger. It's 15,000 people from around 90 countries from all over the world. CERN has been historically very active in promoting new technologies. For example, this year is the 30th anniversary of the web, which was invented at CERN. And for this reason and for many other achievements, CERN has been issued a top-level domain in DNS. So the actual website of CERN is home.cern. The main facility that has been built in the years, and the most famous one, is the Large Hadron Collider, LHC in short, which is a 27-kilometer-long tunnel spanning across the Geneva area, built 100 meters underground. This machine is basically a racetrack for protons and lead ions, where particles reach the highest speeds that are achieved on Earth, which means we are 99.9999991% of the speed of light, which is quite an achievement. There is the empty space in the solar system, which means that the particles circulate in a very high vacuum. And during lead-ion collisions, we achieve energies that are 100,000 times higher than the center of the sun, which makes it the hottest point in the galaxy. So there is a very tiny region of space, which is the hottest point in the galaxy, somewhere below the Geneva area. The accelerator hosts 4 main experiments. The 2 most famous ones are diametrically opposed, are CMS and Atlas. They are general-purpose experiments, which means that they can run a wide range of analysis, and they cross-validate their results. They are built using different techniques and methods, so the actual scientific result that they produce can be verified. The other 2 experiments are a bit smaller, and the ALICE is mainly involved in studying high-density and high-energy matter states, while LHCb is trying to explain why there is not as much antimatter as there is matter in the universe. This is a picture of the CMS detector, so it is one of the 2 biggest ones. CMS stands for compact muon solenoid, and it's compact because it's only 22 meters long and 15 meters wide, which makes it smaller than the other experiment, Atlas. It's very heavy because there is a lot of magnetic shielding inside, so it's around 14,000 tons. And it's also composed of the most powerful superconductor solenoid ever built by humanity. It's a very big scientific and technological effort, and for this reason, contributions came from over 40 countries all over the world. How this machine works, it's basically, when it's in operation, the protons pass in this pipe, they collide with each other, and the 2 halves fit into each other and act like basically a very big and a very high-resolution camera. This camera records events at 40 million times per second, which means that it generates a quantity of information which is around 1 petabyte per second, a bit less. And this data is generated for hours in a row during the operation of the experiment, which makes it impossible in any way to store all this data. In order to be able to store some data to be able to analyze it, there are 2 stages of filtering, which are called triggers. There is one which is in the cavern 100 meters underground close to the experiment, which is an ASIC and FPGA farm, where the input is coming in at 440 megahertz and gets out at 100 kilohertz, which leads to to a few terabytes per second of data. These data are then sent to the CERN data center, where there is a CPU farm, which is responsible of decreasing, again, the bandwidth to arrive at around 10 gigabytes per second, which we can then store on disk and analyze later on. The CERN data center is a fundamental part of the infrastructure for analysis and for the fulfillment of our mission. It's, just to give you an idea of the numbers, it's hosting 15,000 servers, 280,000 cores, has a hot storage, which means storage on disk of 280 petabytes, which are the results of the experiments that have run in LHC. Then we have tape for older data and for backup reasons. And just to give you an idea of how complex the campus, the accelerator, and the experiments are, this is a figure from the fiber optics network. We have 50,000 kilometers of fibers deployed. But this is not nearly enough for the researchers' needs of computing. So in the first half of the past decade, a computing grid was developed. This worldwide LHC computing grid, WSCG for short, which is a collection of data centers located all over the world. It's structured in tiers, so the heart of this grid is situated at CERN, where all data are persisted at least once. The initial reconstructions of the experiment results are done, and the data are managed and distributed to the other data centers. The tier ones, which are 14 centers all over the world. They are one in every big European country, 2 in the US, 1 in Korea, 1 in Russia, and so on, where there are backups of data, and where data are, when batch jobs run for analysis, and from where data are sent to the tier 2 data centers, which are 160 data centers, where researchers perform simulation and the final analysis that they use to publish scientific results. The size of this grid nowadays, it's around 900,000 cores and 1 exabyte of data stored, so initial raw data, intermediate results, final results, simulations, and so on. Part of the infrastructure that we offer as CERN to our users is this growing service of Hadoop and Spark clusters. We have 2 main clusters. One of them is critical for the LHC infrastructure. It's used for the sensors and actuators logging. And then we have a general purpose cluster, which is a bit bigger. And we have this new offering of a cloud-based, cloud-native cluster, which means that we have Kubernetes. We can scale up and down and access data which are not stored locally. The community that uses our products is quite diverse. We have physicists who perform analysis on the computing metadata of the computing grid in order to optimize caches, distribution of workloads, and storage. Then there is an ongoing effort to develop new ways to process physics data, which are now which have been historically analyzed with a C++-based framework, very efficient, but is facing some issues in scaling out, and also machine learning workloads. Then there are our IT colleagues who do analytics on data center monitoring data, and computer security, intrusion, threat detection, and so on. And then we have the BEAMS department, which are physicists and engineers responsible for the maintenance and the development of the accelerator itself. And there we have this accelerator, this logging platform, and also logging and analytics on industrial control machines, PLC, basically. So in order to provide a unified platform for every one of these kind of users, and in order to abstract them from the complexities of CERN infrastructure, which in some cases goes back to 30 years, we developed this front end based on Jupyter, where we can let the users either run their Python workloads or access Spark, regardless of whether it is on Yarn or on Kubernetes. They don't care. They only care if they are using HDFS because they want data locality, maybe. Then they can access this distributed file system where we store the various versions of software for simulations and analysis, and then they can access the data. physics data, so the 300 petabytes that I mentioned before, are stored in EOS, which is this custom storage of CERN. And then there is the possibility to access data on HDFS or on the personal storage that every user has. This is what the platform looks like from the user perspective. So they have, as in every Jupyter notebook, they can see their code. We have developed with the GSOC monitoring for the Spark application, and then they can view the results. As I mentioned, a big challenge is to be able to access these 300 petabytes of data, because they are stored in EOS system, which is accessed with a custom protocol called XRD. And in order to be able to read there, we had to implement to extend the HDFS APIs. And then the files are not stored in Parquet or in an industry standard format, but they use this binary format called root, for which we had to develop a Spark data source in order to be able to ingest it into Spark. Now I will present you the work we've done for this pipeline in order to classify the raw data generated by the detector, which is on the left. And then, depending on the topology of the event that is generated from the particle collision, we can put it in one of the three bins and retrieve them and decide whether we want to store them or we want to throw them away. So the problem of generating hundreds of terabytes per second of data, or almost 1 petabyte per second, is the problem that we are facing now, where we have 5 collisions every time the 2 beams cross in the accelerator. But a major upgrade in the near future of the accelerator, which is called high luminosity LHC, means this. 80 times more data will be generated, which means that we have to find ways to be able to cope with this data, to identify what is really interesting and novel for research, and what is actually a phenomenon that we already know pretty well and we are not interested in storing. In order to be able to record the relevant data, so we have to improve the quality of the filtering systems that we use. We want to reduce the false positives rate, because we don't want to store data that is not relevant, not interesting for research. One of the possible approaches that are being investigated is to move from rule-based algorithms for filtering events to deep learning classifiers, which promise to have a much lower latency than what we can currently achieve with the rules, with the algorithms. This means that we have to move this quite heavy analytics workload to the edge. We want to be very close to the experiment, because we want to avoid wasting resources in offline computing and also during operation in order to reduce costs. But the problem that everyone faces when he tries to implement a deep learning pipeline, or in general a machine learning workload, is very well summarized in this picture coming from this paper. So we see that this picture is quite famous, but it shows in the black that the real scientific, interesting, relevant part is very tiny compared to the rest of the data ingestion, the data cleaning, the verification, the serving of the models, and so on. So the highest value that we can provide to our users is to enable them to just focus on the small black part, while we provide them the facilities to solve all the problems that surround the first one. A way that we found is working pretty well for now is to use Spark and Analytics Zoo. Spark is, Spark Summit. It's very, very well known for its ability to process data at scale. And Analytics Zoo is a platform born for Spark, which provides high-level analytics. And for example, for us, the most interesting feature is deep learning, which is achieved exploiting BigDL and TensorFlow. BigDL is a framework that has been developed by Intel for distributing deep learning on Apache Spark. Analytics Zoo solves 2 problems. The first one for us that we developed the service that we are able to integrate with the existing infrastructure, so the CPU servers that we already have, the data access that we already put in place, the data governance, and all the operations that we need to take care of for providing the service. And for users, it's seamless because they can just come with their Keras model that they developed on their own notebook. They just change the import they do, and they can use Analytics Zoo and distribute the training. So the data pipeline that we developed consists of several stages. I will guide you through all of them now. So the first one is to be able to read the physics data and to perform the feature engineering. Then one has to prepare the features in order to be fed into a deep learning network. Then the models are developed, and this is the scientifically relevant part, so choosing the right model topology. And then the hyperparameter tuning. The final stage in our use case is to find a way to distribute the training. We managed to realize this data pipeline using just 4 Jupyter notebooks, one for each stage, using just Apache Spark and Analytics Zoo. So the input dataset is a simulated dataset, mainly for 2 reasons. The first one is that we cannot actually record what happens in the detector, and the second reason is that this input dataset comes from simulations for the detector that will be put in place in 2026, so it's not available yet. The dataset looks like a long list of events. Every event is a 800 by 19 matrix. Every row is a particle, and for every particle we have some physical features, so momentum, position, energy, type of particle. We read this data coming from our external storage, so using the custom HDFS reader and the custom data source. We compute physics-motivated features, so we add some information to the model, and we store them back in Parquet format, which you can then easily consume from Spark and on Hadoop. The feature engineering consists of adding some information to the model. So from these 19 columns that every particle has, we added 14 more, which are calculated on the data that we already have. But this is a way to add a lot of information to the classifier. So it's sort of cheating, basically. And then we had to create a way to sort the particles. It's physics-based also this metric is physics-motivated. And this is needed because we will use also a model that accepts sequences. So we need to somehow to sort this to create this sequence. Feature preparations, which means one-hot encoding of the categories and so on, and the sorting way to the sorting for the recursive layer are all done in PySpark using Spark SQL and MLlib. So this is very straightforward and it's a solved problem. And then the part of the developing the models comes. So the work starts with a very simple feed-forward neural network, which is using the high-level features, so the informations that we know are right, and we add it to the model as input. Then there is another a bit more complicated network, which has a recursive layer based on gate recurrent units. And then the third model we tested was a combination of the two. So first a recursive layer, and then we add the high-level features, and then we have a dense layer and the final result. The hyperparameter tuning is done using Keras and scikit-learn because it's a very easily parallelizable problem. One creates a set of networks you want to test on a small data set, and runs each one of those on a separate executor. So this is a problem which is very easy to parallelize. Then once we found the right parameters, so the number of layers, the number of nodes each layer has, and so on, for the networks, we instantiated it with Analytics Zoo using the Keras API. So here we just import Zoo pipeline API Keras, and we can use the exact same code that we had from Keras. So this is the most simple model, and this is the most complex one with a GRU layer and the concatenation with the high-level features. And it's always the same. You develop the model in Keras on your notebook, and then you move it to the cluster, just changing the imports that you're using. Then the most complex part as far as deep learning is concerned is how to distribute the training. And this is solved by BigDL and Analytics Zoo. So one instantiates the estimator and then fits it, and you can follow the results of the training live. So using either TensorBoard or in the Jupyter Notebook. And then you can store the model for later use when you will actually use it. We did some preliminary scalability tests. We noticed that it's in this range, so we just arrived at 60 cores. It's scaling very well, and we will, for sure, try to expand these results to a higher number of cores and to a bigger cluster. And then the results of the classifier are very high. We see that the best performing one has achieved 0.9929, which is a very good result for a classifier. So we have solved the problem of preparing the dataset, training it. The last part that remains to be solved is the model serving, which means using the model to make predictions. There are two ways that we see nowadays to solve the problem, and probably both of them work. The first one is to use Apache Kafka as a streaming platform to feed directly into Spark, load the model from disk, and serve it with Analytics Zoo. And this works well, but has some limitations to the scale at which you can actually run this infrastructure, which means that for smaller experiments, something like this can really work. And then there is the second approach, which is a bit more conservative, which means just replacing the algorithms that are inside the filtering pipeline nowadays, and to replace them with these deep learning classifiers, which means that you take the model, which is a set of nodes and weights, you write it in RTL, and you send it to the FPGA, and you just replace the old FPGA with a new one running with a higher accuracy or lower latency, as you can tune these parameters, of course, as much as you want. In summary, I showed how we managed to develop a deep learning pipeline from end to end using already existing infrastructure, which means Apache Spark and the CPU servers that we already have in our data center. We showed the very high accuracy results that we managed to achieve, and these results are very promising and will be investigated further in the future. We show how Spark, Python, Analytics Zoo concur in solving the problem of providing intuitive APIs to our users. We have this problem that we are a training center. We have a lot of replacement of students that arrive for their thesis or their PhD, and we move on a few years later. So it's very useful to be able to provide them tools that are used in the industry, and also very easy to learn because they can be productive right away. And then the reason why we chose Analytics Zoo, it's because it really allows us to use the existing CPU clusters without any modifications to the software, and also because as I mentioned, the APIs are the same as of Keras, so are the ones that every student that is playing with deep learning already knows, and what he has been using while he was studying. I would like to thank my colleagues at CERN, my colleagues in the CERN Open Lab project, the teams that developed Analytics Zoo and BigDL and help us in tuning it, and also the authors of the article on which this work is based, on the preprint, which is topology classification with deep learning to improve real-time event selection at LHC, because they provided the dataset and insightful discussions on the issues they found and how we could help them into improving the analytics and to integrate the pipeline to be able to focus on actual scientific research. Here are a few references about the tool that we use. There is the link to GitHub, and then there is the link to our notebooks. I suggest you look into this repo because it contains all the code that we have, and it's agnostic with respect to our platform. So you just need the Jupyter and the Spark cluster to be able to repeat the analysis that we did. Thank you very much. If you have any questions, I'm happy to take them. We have 5 minutes.
If you'd like to ask a question, there are microphones over here. Please come over to the side and ask at the microphone.
Thanks. Hi. So
Hi.
I actually have 2 questions for you. The first is possibly explained in your paper, but I haven't read the paper, so maybe you can give me some insight. It looked like your model was highly tuned to TT-bar physics. And so can you talk about whether you feel like you might be throwing away any other very interesting ground-shaking physics by focusing on TT-bar?
So first of all, I'm not a physicist, so I didn't write the article.
Okay.
But what they did is that of these 3 models, the second one, which achieves very good results, has no additional information than what is generated by the simulator.
Okay.
So there is no pollution, let's say, in what we already know. But if you want to go to higher levels so if you want to be even more independent from the physics that we know, you would need to use an unsupervised network. No, there are efforts to go beyond what we already know, employing unsupervised networks, but it's not what we are doing.
Right. So, I mean, the concern back when I was working at Slack was when we started looking at doing this kind of machine learning, way back in the day, that the results would be inscrutable, and then they would filter out things that we weren't specifically simulating. That we would basically figure out, what our forward calorimeters would look at, what our various other bits would look at, and then you would say to yourself, well, what are the kinds of physics I want to explore with this machine? And then you would try to simulate what you think you might see, but then there was always the concern you're missing out on something that has an entirely different signature than...
Yeah, but I see your point, but the problem is independent of this work, because even if you use the rule-based algorithms...
the technology is great. I like it.
But I mean, you already have this problem nowadays. I mean, there is a big concern in the physics community that we cannot see anything we don't really expect already, so we cannot go beyond the standard model because of these limitations, that we add the preconcepts that we have in how we do the filtering and how we analyze the data. So this problem of contamination is already there, and there are efforts to go beyond the standard model, but this is not facing this problem.
Okay. Second question was, this is an Intel kind of sponsored talk, and it was done on Intel servers. Were there other Intel technologies that you sort of played around with and used, such as the Intel, math kernel libraries and various other optimized, stuff for running on Intel machines that you can comment on?
No, we didn't, but we have the laboratory in which I'm at CERN is working with CERN since many years, and is for example, they optimized, these clusters were optimized in the past with the Confluent, I guess it's called, this tool to optimize the Xeon servers.
Okay.
Yeah.
Thank you.
So yes, it uses Intel Xeon because BigDL and Analytics Zoo is leveraging Xeon.
Okay. Thank you.
Hi, I saw that you're using recurrent units in this, and I wanted to just understand a little bit better what that's used for. So these are obviously jets in like a hadronic calorimeter. Are you doing recursions on like moving backward through the particle showers in the hadronic calorimeters? Like what's actually being, what is the sequence of particles, I guess?
Sorry, can you please repeat the question?
I'm wondering how the recurrence works in the network. Where what is the actual sequence of particles that are being fed in?
There is a distance which I don't know by heart, but you can find it in the article. So there is this metric that is used to sort the particles, and then you feed the particles one by one inside the sequence network.
But so are all of these particles from the same shower, or are these independent? Okay, so
yeah. For every shower you keep for every event you keep some particles, and then you feed them the most energetic ones, and then you sort them and feed them into the network.
I see. So you are kind of like tracing like through the chains of showers, I guess, for each recurrence.
Yeah.
Okay. Thank you.
Hi. Thank you for the talk so much. At the beginning, sort of, you had mentioned that there's research being done into putting sort of like, I guess, like edge devices on as in the experimental setups. So I'm just wondering, how far along is that sort of thing where you might have like edge ML happening at the actual sensors? Because like I could envision that really increasing the amount of data or information from data you could capture or insights just based on, getting more than 1 out of 40K events. Because a sensor by itself would pick up, many of the 40K, right? But not actually transfer more than like one of those at a time. Is that what it is?
Can you please repeat the question? Can we just discuss it afterwards, because we finished the time and we can meet.
So we are looking to integrate. We are looking for a library, deep learning library that will integrate well with Apache Spark. And I know that you guys have chosen Intel BigDL, which sort of says that it integrates very well with big data as well as neural networks. What I would like to know is that what are some of the challenges that you guys has faced while working with Intel BigDL, and why did you choose Intel BigDL instead of something else?
So the short answer to this is we only have researchers have GPUs in their own office, but the clusters are only CPU clusters. So we needed something that was optimized for CPUs. And the main issue we found is that since you need to synchronize very often the results of the training, it's very important to have a cluster which is as clean as possible, and which means that there are no nodes that are more slow than others, because then they become stragglers. And so we have to try to always work on the same on similar processors in order to not waste time waiting for the results of other executors.
Any other things that you have noticed in terms of performance, or in terms of executors running out of memory, or some crashes? What is in terms of reliability with Intel BigDL?
We had some difficulties in tuning the learning rate, because at a certain point we had the divergence in the convergence of the model was not converging, but that's a general issue that you always have if you have too high learning rate, then you face these issues. We can discuss it later if you want.
Okay, sounds good.
Actually, on that note, thank you so much, Ricardo, for this great presentation. I'm Fari with Intel. There is a booth, there is a demo for the CERN, what we just talked about in the Intel booth. So you can visit the Intel booth number 100. There's a kiosk for the CERN technology, so you can have more questions, Q&A with the team. Thanks again.
Let's give Ricardo a big hand.
Thank you.